Okay, the system initially contains 8 transfer functions labeled as G1, G2, G3, G4, G5, G6, G7, G8. The input of the system is of f of s, and the output is x of s. The blocks are connected using cascade connection, zooming function, parallel branch, feedback paths. The transfer function is f of s and 1 ms squared plus bs plus 1, and the output is x of s. This system is a transfer function correspond to the classical mass spring damper system. X of s over f of s equals 1 over m is squared plus b as plus k. In this case, the parameters are m equals 0.97, k equals 1, the damping coefficient is related to the damping radio using the equation b equals to lambda omega n m, where lambda is the damping radio, omega n is the natural frequency.
In this simulation, you analyze a mass spring damper system. First, in the graphic of the system, you observe an oscillatory response that little by little became stable, which showed a subampered behavior. Then in the step response of the plan, it was seen more clearly the overshoot and the time that the system took to reach the steady state. Finally, by varying the damping factor with different values of EI, it was compared that with lower damping there were more oscillations, while with higher damping the response used more swap stable. These allow a visual comparisons of how the dynamic behavior of the system changes.
In point G, we analysis how the damping radar set 0 affects the system response. Negative 0 makes the system unstable, 0 cause continuous oscillation, and positive values produce stable response. In point H, we add the gain K. In cascade, K only changes the amplitude of the response up, but it does not change the dynamic of systems. In point I, we compared the open loop and closed loop system. The closed loop system responds faster but was more overshot. Final point J analysis restable. The K conditional is the damping rate must be greater than 0 for the system to remain stable.